All right, let's dive right in. Today we're exploring marine zoogeography, which is really just the fascinating science of why fish live where they do. We're about to go on a global tour to map out the invisible borders that shape all life in our oceans. So here's our game plan. We're going to start by uncovering the ocean's biggest yet totally invisible walls. Then we'll take a plunge from the sunny surface down to the crushing deep. After that, we'll travel across the globe, from the super vibrant tropics through the productive temperate zones and all the way to the icy poles. So here's the central puzzle, right? The oceans are basically one giant connected body of water. So why can't a fish from the Caribbean just, swim over to Hawaii? What's actually stopping them? Well, the answer is a lot more complex than just bumping into land. Yeah, you see, unlike fish in rivers and lakes, marine fish aren't really held back by physical things like continents. The most powerful forces that shape their entire world are things you can't even see. And the number one factor, the absolute most critical invisible wall out there, is water temperature. Seriously, for most marine fish, a few degrees difference in the water can be as impassable as a continent. It dictates their metabolism, their reproduction, their entire life. But of course, it's not just temperature. Think about it. Massive stretches of deep, open ocean can be like a desert for a little coastal fish. Salinity, the shape of the coast, and especially ocean currents, which can act like highways or total roadblocks for tiny fish larvae, all of these play a huge role in drawing the map of marine life. Okay, so before we travel across the globe, let's travel down. The ocean isn't just one big uniform habitat. It's layered, and fish have adapted to live at very, very specific depths. We can pretty much group marine fish into three main categories. First up, you've got the shore or shelf fauna, living in those relatively shallow waters over the continental shelves. Then there are the pelagic fish. These are your open ocean wanderers like tuna and sharks. And finally, you have the deep sea fauna, living in that dark, high-pressure world way down below 200 meters. Now, what's absolutely fascinating here is where all the variety is. Over half, 50% of all known marine fish species are shore and shelf fauna, all packed into that thin little coastal strip. Their biggest problem? They just run out of coastline. Meanwhile, the pelagic and deep-sea fish have these enormous territories, but they make up a much smaller percentage of species because they're facing huge challenges like crossing temperature zones or just finding a meal in the pitch black. All right, time for our world tour, and we're starting in the warmest part of our planet, the tropics. I mean, these are the absolute epicenters of marine biodiversity, where that warm water just fuels an incredible explosion of life. Now, scientists divide the tropics into 4 distinct regions, but as you can see, one of them is in a league of its own. The Indo-Pacific is the largest and, by far, the richest. A big reason for that is its sheer size and its complex web of islands, which is a perfect engine for creating new species. It's got pretty much all the fish families you'd find in the other 3 regions combined, plus a ton that are unique just to it. And even within one region, you find these incredible pockets of specialization. Take Hawaii, for instance. It is so isolated that about a third of its reef fish are endemic, meaning you can't find them anywhere else on Earth. But what's just as strange is what's missing. Groupers and snappers, which are the dominant predators on most other Pacific reefs, are almost completely absent. Isolation really does drive some unique evolution. So what separates these rich tropical zones? It's those invisible walls again. The landmass of the Americas. It's a nearly complete barrier, blocking 98% of species. But look at the Eastern Pacific Barrier. That huge, empty expanse of deep ocean is almost as effective as a continent, stopping 86% of coastal species from crossing. Even the Mid-Atlantic, which seems like an open highway, still blocks over 70% of species. Okay, as we leave the wild diversity of the tropics and head for the cooler waters to the north and south, the whole story of marine life just flips on its head. Welcome to the temperate and boreal zones. So here's the crucial trade-off. What these regions lack in the sheer variety of species, they more than make up for in just staggering abundance. It's often fueled by this amazing process called upwelling, where deep, cold, nutrient-rich water comes to the surface, creating these incredibly productive ecosystems. And those massive schools of cod, herring, and flatfish, they support the world's most important commercial fisheries. Now, if we compare the 2 northern temperate oceans, we see some really fascinating differences. The North Pacific is incredibly rich. It's the most diverse area outside the tropics, and it's dominated by groups like rockfish and sculpins. The North Atlantic, on the other hand, is less diverse but has a really strong connection to the Arctic fauna, which is something the Pacific doesn't really have thanks to the narrow Bering Strait and past land bridges. And down south, the story is all about connection. With less land in the way, ocean currents can kind of circle the globe more freely. And this has created these clear genetic links between the fish of southern continents like Australia, South Africa, and South America, which hints at a deep shared ancestry, even though they're thousands of miles apart today. Our expedition now takes us to the absolute harshest marine environments on the entire planet, the Arctic and the Antarctic. Here, life is just clinging on in the face of some extreme, relentless cold. At both poles, the near-freezing water temperatures just severely limit what can survive, so you get extremely low species diversity. But the dominant players are totally different. The Antarctic is the realm of the nototheniids, or ice fish, some of which have antifreeze in their blood. The Arctic, meanwhile, is home to sculpins and relatives of cod. And the poles reveal one of zoogeography's most curious patterns, something called bipolarity. This is when you find the same, or very closely related, species in the cold waters of the north and the south, but they are completely missing from the warm, tropical waters that separate them. And here's a perfect, almost unbelievable example. This deep-sea anglerfish has been found way up near Greenland in the north and all the way down in the Antarctic in the south, with this massive gap in its known distribution right across the entire tropical belt of the planet. So you have to be wondering, how on earth did it get across the equator? Well, the leading theory is that during past ice ages, global ocean temperatures cooled down a lot. This probably created a temporary cold water bridge right across the tropics, allowing these species to expand their range. Then when the planet warmed up again, they got stuck, isolated at the poles, leaving us with this bipolar puzzle today. So, to wrap up our journey, marine life isn't just randomly spread out. It's governed by invisible barriers, and temperature is king. We've seen that life is structured vertically into three main groups. The rich tropics are carved up by massive barriers, while temperate zones are these engines of sheer abundance. And the poles show us life at its absolute limits and reveal these ancient climate connections through that weird phenomenon of bipolarity. And I'll leave you with this thought. We know the Suez Canal is letting Red Sea fish invade the Mediterranean, basically breaking down an ancient barrier. But the single most important barrier we've talked about all day is temperature. As our oceans warm, that great invisible wall is shifting, and in some places, it's starting to crumble. What do you think that means for the future map of life in the sea?